Another one that I haven't been solved, but it's sort of purely academical. Can you come up with an exact problem that has more than a constant speed up? I mean, the best I know is a factor of 2, and I've shown it to you. It's the parity. Also, you might want to study the relationships between quantum and randomized complexity. But the most important one, I think, is what is the power of BQP? For example, can you show that BQP sits in the, for those who know, the polynomial time hierarchy? I have no idea. We know that BPP, probabilistic polynomial time, that sits in the polynomial time hierarchy. What about BQP? If you've never thought about this question, then you will actually, and you would care about it and you would work on it, you will find the proof that it sits in the hierarchy, and actually the next day you will realize it's wrong. So this is what happened to me and to many others.
Have you constructed an oracle under?
Good question. So also it's not known whether there's an oracle where BQP is not inside the polynomial hierarchy. It's even not known whether there's an oracle where the BQP is not in sigma 2. So, where we know that BPP does sit in sigma 2.
Even outside NP.
Yeah, so the best known here is an oracle where BQP does not sit in P to the NP.
Oh.
But there also is an oracle where BPP is not in P to the NP. So that sort of automatically gives you this. There is an oracle where EQP, so when there's no error, is not in P to the NP. So it's not. Yeah. So there's a problem, a relativized problem.
P to NP.
Yeah. It's not in. That is a little bit harder, and there you need these polynomials. Okay. For further reading, you can look at these 2 papers. Where I proved, where we show most of these lower bounds. So summarizing what I talked about is I talked about quantum algorithms, and I've shown to you that sometimes there is an exponential speed up. Factoring is efficient, and there's this database search, this OR, this has a square speed up. That was basically lecture 1. Then in lecture 2 I've shown to you about quantum communication complexity, that also there sometimes you can have exponential speed up. And I talked about entanglement assistant communication very briefly at the end yesterday, which in my opinion, and actually also in some of the physicists I talked to, is a nice explanation, a nice way of looking at fundamental physics questions. And actually there's also more of that going on, where you can sort of take the ideas from computer science and communication complexity and sort of adapt them back towards physics and problems that they have in their foundations. And now today I talked about the polynomial method and how that shows that some problems do not really allow speed up at all, or just a little in the quantum case. Then I want to end by this nice slide of Charlie Bennett. The frequently asked questions. So if you still have any questions not on the slide, you can ask me.
It takes time to read all the list.
That gives me just time to escape quickly. Although you didn't give me a ticket yet.
Does it quantum?
Yeah.
No. Okay,
so we need to wait 20 years before we know that there is no quantum computer.
Maybe.
What they say. It's 20 years for the construction or for the getting the answer. Too early to tell. Maybe 20 years.
Yeah.
No, the question is when. The answer maybe 2020.
So you often get this question like, when is there a quantum computer? Next year or tomorrow?
But when we will know that we will never have it. This is the other question.
It's quite possible.
We will have one. I'm optimistic.
Does anybody has a question which is not on the list? No.
Thanks for inviting me. I really enjoyed it.
Even your
But there is an attitude there, so they
Distracting
consider
remark.
some other question.
what else? But there is no the main answer. What does the quantum information science do? Probably can get a better understanding of quantum.